So we're looking at the propagation of light, basically how light passes and interacts through matter. And we can look at a long history of light and see how our view of light has changed throughout time. Going back to 1000 AD, Euclides was the first to propose that light consisted of tiny particles. We now know today it does. In fact, it consists of photons. Newton also believed this. He thought that since white light could be broken into all different colors of the spectrum, that it must be essentially made of different particles of different colors, and that the prism essentially sorted these colors out. However, in 1678, Christian Huygens was able to explain many of the properties of light using waves rather than particles. So a shift in our understanding of light changed from thinking it's made of particles to maybe it's made out of waves. Young performed his famous double slit experiment, and this certainly showed that light did have a wave nature to it. He was able to show that through interference, constructive and destructive interference, that light had a wave property. And this was also confirmed by Maxwell, who predicted through his equations that electromagnetic waves should be able to be produced. And this was, of course, confirmed by Hertz. Einstein got the pendulum swinging the other way again. The photoelectric effect was explained by Einstein as being particles of light. Basically, a photon would come in, free up an electron, release the electron, rather than the wave aspect of light. And eventually, Planck also showed the quantized nature of oscillators which produced blackbody radiation. And it was soon accepted that light had this dual nature. It was both a particle and a wave. In terms of the particles themselves, the photons, are basically little packets of energy which do contain electric and magnetic fields. And we say that the energy of the photon is equal to HF, Planck's constant, 6.63 times 10 to the minus 34 joule seconds, which can alternately be written instead of F. I think in introductory physics, we like to use F for frequency. In other courses, we like to change that to the Greek letter nu. It basically means the same thing, that the energy per photon is equal to Planck's constant, a very small number, times the frequency of the light. And again, we can demonstrate the dual nature of light. However, it's hard to simultaneously show that light is both a wave and a particle. In the case of interference and diffraction, we can see that light isn't stopped by a barrier like particles would be. If you simply place a barrier in front of the particles are going to stop and not be able to propagate any further. However, with a hard edge, we actually see that the light waves will propagate around this edge through diffraction, and we can observe this. We'll talk about this in the following chapter, how diffraction takes place. Of course, Einstein's famous explanation of the photoelectric effect led to the understanding that light was also composed of photons. What about the speed of light? The speed of light is famous because it is the fastest possible speed that we have in the universe. This is something that was actually measured through astronomical means before we could measure it on Earth. ROEMER became the first person to measure the speed of light with the help of Huygens. And what he was able to do was observe that the moon Io would go through a little bit of a time delay in terms of the eclipses that would make in front of Jupiter, depending on where it was relative to the position of the Earth. As the Earth approached, times would speed up, so the difference in times between the eclipse would become less. If the Earth was receding from Jupiter, the light would take longer to catch up with the Earth, and this would make the eclipse times somewhat delayed. Using the speed of the Earth around the sun and using the eclipse times, Christian Huygens was able to use ROEMER's information to estimate that the speed of light was somewhere around 2.1 times 10 to the 8 meters per second. That's not bad, considering that the actual or the accepted value for light is 2.99 times 10 to the 8 meters per second. So roughly about a 30% error, considering that this was done simply through telescopic observations. Another measurement for the speed of light, also through astronomical means, was done by James Bradley in 1728 by seeing the shifting of the positions of stars. And this would have to be done with telescopes because the shifting was very, very small, what we call an aberration. The stars would shift their angle in the position of the sky. If the Earth was moving toward them or moving away from them, we would see this slight change in angle. And the angle is related to the ratio of Earth's orbital speed, once again, to the speed of light. On Earth, the first terrestrial measurement for the speed of light was done by FIZEAU. Armand FIZEAU did this in 1849 through a very ingenious method where he would cut the light into pulses using a rotating slotted wheel. Now, this rotating wheel would alternately let light through and then block the light. And the idea here is we would have a light source. The light source would create a continuous beam to the rotating wheel. The wheel would then cut the light into a pulse and then head to a mirror 8 kilometers away. So this is impressive for that time. It would then reflect off of the mirror, and it would have to make it through the rotating slotted wheel when one tooth had moved over a certain fraction of the circumference of the wheel. So it would go through the first slot and then would go back through an adjacent slot, pass through the observer, and when the rotating wheel was just at the right frequency, they would be able to see the light pass through. So really, they're sending the light over a round trip of 16 kilometers. And of course, speed is distance divided by time, timing the rotating wheel from one slot to the next slot, and using the distance divided by time to come up with a fairly accurate measurement for the speed of light. Now, light actually slows down in some media. Why does it slow down? This is a question that I had very early on when I started studying physical science. I could never understand if the speed of light was 3 times 10 to the 8 meters per second, why would something slow it down? Why would simply sending it through glass or sending it through water decrease the speed of light? And we can see that, yes, in fact, depending on what we're sending it through, it will have different speeds. Now, the speed of light in a vacuum is the fastest speed. That is what we typically call c. All these other speeds are not going to be c, but some fraction of c. So for instance, if we send it through air, air is a low density substance. It doesn't interact with the light very much, but we can see that the 1/10,000th of a meter per second is slightly slower. So it's a very, very, can't remember the exact percentage, but it's a very, very small change in the speed of light. Water, however, there's a significant change. Okay, it drops about 30%, or it has about a 30% decrease of its speed. And you can see with glass, it's even more significant. It's down to about 2/3 of its speed. Diamond has the highest index of refraction. We'll talk about what index of refraction means in a second. But in diamond, it's traveling less than half of its speed in a vacuum. And again, I never understood why this was so. Why does light slow down just because it's traveling through a particular media? Well, here is the actual classical approach to understanding what's going on. All of these blue lines represent wavefronts. They're all moving basically at the speed of light. So this wavefront is going to come up and hit these 3 atoms, which are in its way, okay? Now, these atoms act like little oscillators. When they're subject to the electric field, especially the electrons, they're going to oscillate back and forth. And when they do so, they produce their own wave fronts. So for instance, this atom right here in the center oscillates up and down. If you've ever watched a buoy on the water or a bird on the water, as a wave passes through it, they give off their own circular waves. And that's exactly what happens here. The atom is set in motion, or the electrons are set in motion in the atom or in the molecule by the electromagnetic wave. They in turn produce their own wave fronts, and the red wave fronts combine with the blue wave fronts to produce a new wave front, which is shown in green. Now, if you look at this right here, we can see that the green wavefront is a little bit behind the blue wavefront, which is passed through. Okay, just a little bit of a delay. So if we think about what these atoms have done, they have given off their own waves. Their waves are slightly out of phase with the original wave. They're slightly delayed in phase. And through constructive interference, the red waves plus blue waves are going to produce a slightly delayed green wave. Now think about what's going on right here. Every time the blue wavefront encounters an atom or a molecule, it's going to receive a little bit of a delay. The more atoms there are, the more delay it receives, and the longer it takes to go through the medium. So it's the interaction between the wave and the atoms which is actually making the resultant wave travel slower. The blue wave travels at the speed of light, okay? But it's that phase delay from the secondary waves produced by the atoms, which are going to slow it down just a little bit. And we can see that in this representation right here. The blue wave, it is the original electromagnetic wave. It's originally traveling at the speed of light. So its peak is going to travel at 3 times 10 to the 8 meters per second. But the red wave is fallen behind the blue wave. It's out of phase. So the combined effect, the superposition of both waves, produces this green wave, which is just a little bit delayed. So the more material it goes through, the more time delayed it receives, and thus the light travels slightly slower. So think about this. It's not the electromagnetic waves themselves that are propagating slower than the speed of light. It's the interference effect that makes these peaks and valleys propagate slower through the medium. Okay, why does light slow down? Again, essentially because there's this interaction between the original light wave and what the atoms are doing. Now, we call the ratio of the original speed of light, what it travels in a vacuum, what the primary wave would be doing within the material, and the new velocity due to this interference, we call this the index of refraction. So in most materials, the index of refraction is actually going to be 1 or more. There's some cases, and these are very, very rare, where the index of refraction can be less than 1, but it doesn't mean that anything's traveling faster than the speed of light, other than the peaks and valleys are traveling faster than the speed of light. Okay, again, very, very rare cases that this happens. So it is actually the phase information that's traveling faster, but the photons, the light still travels at c. If you were to put a beam of light, a pulse of light into one of these materials with an index of refraction less than 1, it would still take, it would still be delayed due to the speed of light at 3 times 10 to the 8 meters per second. Okay, probably not explained the best way there. But again, we're going to assume that most materials that we deal with are normal materials where n is equal to 1 or is going to be greater than 1. So because the index of refraction, all right, depends on the speed in the material, it's also going to change how the rays travel through the material, okay? We'll explain how this happens, but it refracts the light. So if a beam is coming in like this, the part of the wave which is on the top side, let's say the part of the wave which is here, and compared to the part of the wave which is on the bottom side, the wavefront, that's going to be delayed slightly more than the part on the bottom, and that's going to change the direction that the wavefront travels, and therefore it's going to change the direction that the light propagates. And then when it leaves the slower material, the higher index material, it's going to continue on its original direction if the index of refraction is the same. So we call it the index of refraction because the greater the index of refraction, the more the material will tend to bend the light as we go from a lower index of refraction to a higher index of refraction. Now, here is the index of refraction for a number of different materials. And let's try to make sense of exactly what's going on. Air, as we said, has a very little impact on the overall speed of the wave. There are very few molecules there to interact with these waves as they're propagating through. So we tend to see a very slight, very, very small decrease in the speed of light, and therefore an index of refraction very close to 1, but maybe just a little greater than 1. Water has nearly 1,000 times the density of air. Also, water molecules interact with the electromagnetic waves a little bit more than the air molecules do. And therefore, the index of refraction is much greater. Now, ice, you'll notice, has a lower index of refraction than water. Does that make sense? Absolutely. Ice is less dense than water. The molecules are spread out more. So the delays that are taking place per volume are going to be less. Thus, the index of refraction is also going to be less. The other materials tend to be solids. Fluorite is a very low index of refraction glass, which is oftentimes used for specialty lenses. Fluorite lenses are used in some types of telephoto lenses where you need a very low index of refraction to balance some of the other glasses that are used in it. I'm not sure that fluorite is hygroscopic, but it does have the advantage of being a lower index of refraction. Quartz, pure silicon dioxide, has a fairly low index of refraction as in terms of transparent materials. Most glass that we have is not pure silica. Most glass that we have is made up of some combination of silica, and in this case, alkali oxides, meaning adding sodium. Usually, potassium is more oftentimes used. They also use boron. They'll add boron to create borosilicate glass, which is also considered to be a crown type glass. I'm not sure about the origin of the term crown, but typically a crown glass is going to be a lower index of refraction glass. Flint glass is usually what is called lead glass or lead crystal. It's a combination of silicon dioxide and, if it was made years ago, lead oxide to give it a higher index of refraction. The lead oxide has a higher index of refraction than silicon dioxide because the lead tends to interact with the primary wave much stronger than the silicon dioxide does. Today, we replace the lead with other materials such as titanium to produce the higher index of refraction. Titanium oxide is a mineral we call rutile. And if we want a really high index of refraction, we increase the ratio of either lead or titanium or some other material, those oxides with the silicon dioxide. Zircon is another material which is transparent. It is zirconium silicon dioxide hydroxide. Diamond has one of the highest indexes of refraction at 2.42, and the material with the highest index of refraction is moissanite. Although moissanite is a naturally occurring mineral, Most night that you're going to come across is going to be lab created. So we look at these different materials and we think about the index of refraction. What is going to slow down the light? Well, the more atoms you have in a material, okay, usually denser materials are going to slow down the light more, but it's also the composition. Some materials have stronger resonances at the frequencies that we have in the visible spectrum, and therefore, when the electromagnetic wave comes through, they're going to oscillate stronger, produce more intense secondary waves, and therefore create a slower propagation speed, create a larger index of refraction. Now, glass is a term that's used for material without any definite crystal structure. We use the term glass to talk about anything that is amorphous. It doesn't have a crystal structure to it or a definite three-dimensional arrangement to it. But it's also a term that we use in optics to refer to anything that's fairly transparent. Now, here's the optical transmission of a typical optical glass that would be used. I'm not quite sure what this is, but I would assume it's probably some type of crown glass. And as you can see here, if we look at the wavelength of light, which probably spans, somewhere around here, we can see that's fairly transparent to visible light. Again, I'm sort of approximating where it's going, but we also see that there's a good long window where it's also transparent to some wavelengths of very near infrared light. Now, the term greenhouse effect comes from the fact that in a greenhouse, glass tends to block the longer wavelengths of light, the longer wavelengths in the infrared, from escaping and re-radiating out into space. So visible light comes in, it's absorbed inside the greenhouse, and then the glass tends to block the far infrared from escaping, making the greenhouse much warmer. And again, here's some different types of glass. As we said before, crown glass is typically about 10% potassium oxide, and then the rest is silicon dioxide. Again, borosilicate glass can replace the potassium with boron, but they both have very similar properties. We don't like using pure silicon dioxide, what we would call quartz, because it tends to be more brittle, although in some cases it's better than crown glass because it's transparent in the ultraviolet part of the spectrum. It is less flexible. It's just harder to deal with than pure silicon dioxide. So crown glass 1.52, and again, flint glass. You've probably seen fine stemware, which is made out of what they might call lead crystal. Again, we don't really produce a lot of lead crystal anymore because of lead's toxicity. Again, we tend to replace this with other materials such as titanium dioxide, zirconium dioxide, and even lanthanum oxide, just because these materials have a lower toxicity. I know some people are actually not so keen on using antique leaded crystal because their concern is that if you try to store anything in the lead crystal, or you drink out of lead crystal, some of the lead will leach into the beverage that you're drinking. But as far as I'm aware, in most cases, even though it's lead oxide, it's pretty much chemically inert. The lead's bonded with the oxygen, so it's not going to leach out. Again, diamond, pure carbon, has a very high index of refraction. And when we talk about total internal reflection, we'll see that this property of diamond with a very high index of refraction makes it behave very differently from glass. A trained eye can clearly see the difference. I don't even think you need a trained eye. You can clearly see the difference between the way a diamond will reflect the light back to your eye, compared to just simply a cut piece of glass used as a rhinestone. Now, throughout this chapter, we're going to be using the ray approximation quite a bit. It's hard to represent light propagating because really, when we think about light propagating, it's propagating with different wave fronts, which have different phases. So for instance, we could imagine that these blue planes here represent the peaks in the electric field. So maybe if we would show the electric field as a function of position, for these wave fronts, it might look something like this. However, sometimes it is sufficient just to show these arrows, which are normal to these wave fronts, these rays, because all we really want to know is how the light is propagating. And the rays are a pretty good approximation of how these wave fronts are going. Okay, there are some limitations to the ray approximation. The one thing that you'll have a problem with the ray approximation is when you get them to converge, the rays converge to a point. In reality, through diffractive effects, light can't converge to a single point. It actually has a spot size. But the rays do a pretty good approximation, allowing us to see how an image might form from a lens or a optical system with many lenses. It helps illustrate how our eye will perceive objects in different optical systems. For the most part, we can get a lot of the very basic information that we need in geometric optics using this ray model.